Hello everyone, this is Francesco Foncellino from Analog, MEMS and Sensor Group of STMicroelectronics, and I will present a thin film circular diaphragm for the implementation of a MEMS-based resonant mass sensor as a candidate for detecting particulate matter in air. Our prototype of the clamped circular diaphragm has a diameter of about 600 microns, and the schematic section is depicted here on the left side. We have a thin film of a silicon layer with on top of it an active stack made of two metal electrodes and a piezoelectric materials in between. Such membrane shows a vibrational spectrum depending on the characteristic properties of the materials involved in the structures, and we measure the vibrational spectrum by using laser Doppler vibrometer, and we acquired the spectrum of the first three resonant modes. Our study is based on the mass loading effect. When you add an extra mass on its surface, we provide a change of its mechanical properties and consequently the change of its vibrational spectrum. The frequency decreases, and if the extra mass is smaller than the effective mass, the frequency shift is proportional to the extra mass. And here we report an example of the spectrum is acquired before and after loading the extra mass. We used certified microbeads to load the membrane with given extra masses for each trial. We put microbeads on top of our membrane and acquire the vibrational spectrum plus a picture of its surface. Each loading trial is then deeply analyzed and the pictures are sorted, rejecting those unsuitable to be subsequently analyzed. We derive the number n of loaded microbeads by processing the acquired images by using a customized code. Once we derive the number of microbeads, we can calculate the cumulative mass of the whole particle distribution thanks to the known density of the silica. At this point, we know both the added masses and the corresponding frequency change. In this way, we can correlate both data. On the right, we report an example of data acquisition with 743 particles corresponding to about 97 grams, and the shift of these resonant modes equal to 625 Hz. The complete set of the acquired data is reported here on the picture on the top right side, where the frequency shift data for the first three resonant modes at different loading steps reported. We reported the parameters in the table, and according them, we can derive the sensitivity for the first three modes. In particular, focusing on the first mode, we get a mass sensitivity of 5.5 Hz per nanogram that is coherent with the data present in literature. In conclusion, we showed that a piezoelectric MEMS membranes can be used as a resonant mass sensor. In addition, the frequency shift measurement is valid for all modes, and in particular, we focused on the first three modes. And the sensitivity is proportional to the frequency of each vibrational mode. In the next steps, we will measure the impedance frequency spectrum to validate the mechanical counterpart. In addition, we will evaluate the impacts of the interference, such as the humidity and temperature. And finally, we will evaluate the sensitivity of structure based on different piezoelectric materials. Thank you for watching my presentation, and if you have any question, clarification, do not hesitate.